Okay, so I posted a video called "An Animated Zoo of Fractals and Chaotic Systems" last year. I believe it was released on uh, it was released last September, and the aim was to create a website that includes a bunch of fractals and chaotic systems and their animations, and I'm also going to show the the actual code that's generating the animations and the visualizations. So um, this website called a gallery in fractal dimension is what I made during this month, and it sort of covers. So if you go to collection, it sort of covers a bunch of different types of fractals, and with and what's important is that I classify them with 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 mathematical ideas just instead of descriptions of what they look like. And I I'm gonna introduce to you the several different types of fractals, like actually several different types of way that we can create fractals, that a human being has been able to create fractals, or more technically speaking, uh, it's they are like different views of fractals. Um, so the first thing we did is we'll skip the parts of. Okay, so the first part I did was for the Lindenmayer system, and it was first created to model those IFS system, like iterated file system. And I so these two linear system fractals are probably the easiest example that you can find on any mathematical tutorials. One is called the Koch curve. So it's showing the process that they evolve. Sorry about the ad. Uh, and the second one is the modified curve, Koch curve, which you can see from here. You can see from here it gets somewhat more complicated as you go along, and the process of the iteration is that you take a string, so you take uh, so if you take a string that says go forward, turn left, go turn right, and turn right, and go forward and turn left, and it's going to then you could always find some kind of mapping that could transform those that could perform transformations on the string system, so that they could actually translate the f plus f minus f plus f into the basic form. And for each iteration, you can what you can do um, is to replace each part of the is to replace each part of the line segment. Say for this, I replace this by forward, turn left, turn right two times, and forward, and turn right, and then turn left and forward. You could in this way you create an iterative file system, so that the parts get more and more complicated as you go along. But and uh, and the limit of the plot, by saying by limit, I mean take iteration time, which is the discrete time. Take the discrete time of take the limit of the time of iteration to infinity, and you could calculate its fractal dimension. So this curve is it is a bunch of line segment, but when iteration time goes to infinity, you get every every line segment is connected to a little a tiny. You could imagine that every piece of this line segment is connected to the next line segment, and when iteration times goes to infinity, um, and you would have infinitely you have infinitely more the number of line segment, and we call it curve, but it's just a special way that people name it, and you could actually calculate the fractal dimension of this curve. It's it dimension it's dimension because it has a rough surface, and whenever you zoom in the system, it's always gonna show you the same. Um, it's always going to show more details of the form. Um, so it has the factor. It has a non-integer dimension, which is fractal dimension, and the way I created the plot is by using this package called the Linden Mayer um, a package in R. But here's my here's my branch of the Linden Mayer R, or you could go to the original thing, and you could actually see I made a pull request. I've submitted a pull request to this to um, modify and simplify some functions, and updated the documents for you. So and what the function, and you could install and then you install into the package into R, but and and you could and you could and read manual, and you could easily create this with limited you could first do the example. I'm not sharing the code because the 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 fractal is created with with very basic examples, and so the basic function for this is to create a to the our system with turtle graphics. But what is different what is different on the what is different in the new version is that um, we could actually we could actually not plot this. Actually get a we could actually get a string of those f to those characters, and we can convert it to a data frame that stores the coordinates that could store the coordinates, and the index of the iteration, and then you could use whatever and then you could use whatever graphic package you want to plot it, like namely OpenGL, or you could you could also you could also do this using ggplot2, which I demonstrated the possibility uh, which I demonstrated the possibility there, so that the advantage of using ggplot2 is that you can get some kind of color map to indicate to indicate which what index the specific line segment is on, so that if you ever read the book by Hans if you ever read the book called Space Filling Curve, you get an idea that we could actually find some kind of function that maps an interval of real region from 0 to 1 to an era and the and if you could imagine that this color map is on the scale 0 to 1, but this is from 0 to about 3,000 or something, because because this n is showing how many steps have we gone to reach a specific point, and it takes a bit of time to actually create these, and ggplot2 is optimized for its speed instead of memory usage. So sometimes, occasionally we can have the problem of having too many line segments, and you don't really have enough memory to plot it. Uh, but it works fine if you don't set it to ridiculous large um, uh, iteration times. And I believe I was planning to do the algorithmic beauty of plants, but so far I haven't got time to finish this part. I've only got a few examples, but um, uh, I think and I think you could easily recreate those plots by using similar codes, and we did, and I had mentioned the logistic map and tent map, and I did a bunch of other mappings. Um, so this is showing the cobweb of the mapping. So say for example, I got an equation. I got an equation, uh, y equals to 1 minus absolute value of x times lambda, and I change lambda a little bit to animate this, but uh, I can start from somewhere on the x axis. So this is so this collection of line segment actually represents the process that a nonlinear difference equation is going to give me. Now, um, from so this is the x1, and it gets mapped by some function f to f of x. So the second point is lies on x1 comma x2, and so you could imagine that this point is going up to meet the curve, and then go horizontally to meet the straight line. Uh, the straight line is always y equals x. You might see the slope changes, but that was because the scale changes when we create the map, and it goes like this. It find the curve vertically, and find the line horizontally, and you could and it finds the curve vertically again, and find line horizontally, and it keeps doing this so that it gets iterated from f of x and f of x and f of x, and its behavior of x sequence changes as I change the value of the parameter lambda, namely the slope of the slope of the nonlinear map, and from from there we get the system converge to one station point, and then we begin to bifurcate. Bifurcation is the process that the dynamical system the dynamical system go from one type of solution, say a stationary point, to another type of solution with the change of the with the change in parameter. So this is going from one fixed point to a periodic solution, and it's going to sometimes it doesn't quite it's never going to quite converge, and um, it could be and this could be it could fill some areas, and this could be pseudo periodic or completely aperiodic, and sometimes and people used to create random numbers using this property, but I don't believe the random number generated now is using this, but uh, at least people used to, and there's some interesting behavior. So like it occasionally gets back. You know the at some point we may have a point that the complicated behavior gets really simple, but one thing that we should get the one thing that we should get really careful about using visualization is that usually we use float numbers to represent the values. So there can always be some errors, and those errors can accumulate, and conversely, some important difference could disappear. So that when you type zero in the computer, it's never quite zero, and when you type one, you always get a small number, a small epsilon, uh, because of the type of the storage of the float number. And for the chaotic system, this error could matter. So it's not a small error in iteration could cause a great difference in the behavior. So visualization in there is just a tool to get a sort of intuitive way that we can um, see the numerical result of this. We could say this is a simulation, but never quite the real behavior of the chaotic system. And still it's useful because you never create almost never create or people never like create a chaotic system by hand because it's too it takes too much time to calculate those iterations. So it still tells you a lot of things about the system, um, but it's not up to the state that we can come to that we can come to a proof that guarantees that the system behaves in this way. We 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 will always want a more technical proof instead of just a graphical intuition, and and this is important. And one thing I forgot to mention is that the interesting part about using ggplot2 or using equivalent grammar of graphics um, packages is that you could create mapping from values to colors. So what I'm using in this plot is that I'm using color to represent the the index or iteration steps. So the red colored lines are closer to the convergence. So if it converges, it converges onto a red point. So and the blue lines are just the blue line segments are just the process when we are converging when we are calculating the sequence. And you can see it gets more complicated when the function has more than one peaks. What I mean by that is that we can have some more complex functions, like say cos x x assigned to cos lambda of x, and you can see some more complicated the jumpings. But if you stop the video by at some part, you could still see some basic patterns, like this one is converging, this one has some kind of periodic uh, period doubling bifurcation, maybe periodic doubling bifurcation. We could we need um, technical proof to see that, but this plot give us some kind of intuition. So that the critical points of a different system, or the stationary point or the stationary orbit of the difference equation can actually jump from one place to to another place, and you could have those more like complex behavior, but they're more like behavior that one is built on others. So in this way, we can not only classify, in this way, we can not only identify what is where there's a stationary point, or where there's a periodic solution or aperiodic solution. We can get some kind of inspiration to construct our own complex dynamic system. What I mean by that, is that you could create some art out of it, but that's not quite related to mathematics, and so we will stop when it gets overly complicated. And all right, it's not true. We could do this for fun, but I but I but I wanted this visualization to have some mathematical meaning and give you some kind of intuition. Right. So this is cos lambda times x, and this is mapping this black stuff is y equals to sine lambda times x, and you could see that by changing the parameter lambda, it gets quite different from here. Just so I think it creates better illustrations than those we have seen on those textbooks. Okay, so and it does have some kind of application, but we I don't know, there's still some works to. Okay, and so far we used a difference equation to create iteration. So this is to assign x to a value of to a function of x. You could always, and you could also create a system of difference equations. Say x and it has x and y, and each time you assign the new x to some function of x and y, and assign a new y to a new function of x and y. But and I've actually came up with an idea that can create some kind of visualization that's in analogy to cobweb. We can have two surface, and we could have lines going around the surface, and I know the plot will be quite messy, but I hope that in some cases that would be a little bit more helpful than those scatter plots. And you can see the source code from here, which is called 1D mapping explorations. And if you and this is the part and this is part where I create a tint map, and say you don't really have to know all the programming stuff. It's just all the programming stuff to do this, and all you have to do is to first install this package called it's first to install ggplot2, and then install maybe PSD, the power spectrum estimation. But it's not very necessary. But I made it into one part of workflow to see that if if the system is periodic or non-periodic. Um, so the package to create this is series. Oh yeah, Series Explorer. This is still in development, but you could use dev tools to maybe. Okay, maybe I'll read me. So use dev tools. So those are and install packages dev tools and you could um, and library and you could use the library developer tools, which is quite useful when doing package development. Uh, and install GitHub, uh, basically my username. So this helps the package to find my repository and series explorer and and yeah, that'll work. So you could do this within R, and that's fine, and it would just work. And yeah, if I go, sorry, if I go back to the if I go back to the repository where I store the code that's generating this, you could start by modifying this top level stuff. Say I got another function called sum map, which is a function of x with the parameter lambda, and you type the expression there, and lower bound is the lower bound. The upper bound is ub stand for the upper bound of x. Lb stand for the lower bound of x, and you should have a name of the plot, like say name it tent map, and you set to work directory and you could define a sequence of lambda to create uh, the iteration. So in this way, I always use the lambda from 0 to 2 for those single peak map, and use the 0 to 2, I believe 0 to 2 pi for those trigonometry based functions. And I know and I sort of know that this is like has large chunk of code that's behind it, and you have to use a number of packages to actually create some those beautiful mappings. What we could do is that we could go to this file called map3, and and if you just want to iterate, and if you just want the a cobweb without any fast Fourier transformations or other type of plot, you could maybe copy and paste something, or and feel free to do a pull request to this repository or the repository of series 6 or Explorer. Um, that would help us, like that would help to make this thing better. Or if you have some troubles, just you could like leave some messages on the issues page. Um, so that's the first problem, and and for and for the difference equations, we can have different equations based on the based on complex numbers, and namely we got the Mandelbrot set and the Julia set, which are the two I guess most typical thing we we start with. So I haven't. But if you go to the homepage, there's a because I haven't done this very systematically. I have done the Mandelbrot set with respect to the to the power. You can see z to the power of something plus c, and by changing the iteration expression z assigned to z squared plus c to z to z equals to z assigned to z to the power of p plus c, and by varying the expression p, we can get the get the they call it field contour. It's contour field with color. We can get a field contour animated. But uh, but this I'll probably organize this in a better way in the future. So by the time you see this video, I've done the sorry, I've done this in a separate page. This is called generalized man broad set and relevant contour animations, and we can always do this for Julia set, but Julia sets had different has a bunch of different um, parameters. Say it's like have a real it's a real value of p, imaginary value of p, real value of c, imaginary value of c. But so far I've only done the c within minus with the real value within -2 to 2, and from 0 to 2i, because someone pointed out that there's some symmetry with respect to the parameter of the of the parameter with the x-axis. So so that's the reason I only create like half the plot. And another problem is that when I create the Julia set with the positive p, the some plots just don't show up because they either diverge quickly, or there's some other reasons. So I've only done a collection of those points, and this video is like a quick collection of these, but it's not very organized in that. But it's not very organized in an ideal way. For this, I got probably 100 GB of image files, and it took a month to render, I guess. And I still have the image files, and probably I'll do something in the future to better address this. And for some interesting plots, of this animation, I've done some zoom in videos, but I haven't uploaded the code for the zoom in videos. I just showed you one of this, which shows a bunch of herd which I found from z to the power of -2.0 plus minus 1.4 plus 0i, which is a very strange, which is a quite, I think, quite surprising things to find out. And but as you see when I zoom in the shape, the contour rendering is gonna stop when I have a when I have a matrix that is contained with one value. So um, so as you see the problem is that there are some points that are not very interesting, and some points that are very interesting. And when you do zooming video, you gotta pick a relatively complex point, not just for the not just for being like, not just for your video to be beautiful, but also to avoid the problem of of rendering failure of the contour plots. And that's because the way the contour plots is rendered is it requires some values in this plot in this point at this point to be different from some values from um, the other point, and you could sort of examine this by picking some point and see what's the value there and see what's the value there. But what I'm thinking of is that we can have some kind of program to we can have some kind of program to generate random points and like within some area and automatically find out that whether one point has a different value of the number of iteration needed than uh, as compared to the required value for iteration for a point that have some kind of small epsilon next to it. So so in this way you can examine the whether this point is being very like interesting to zoom in. And what I expect is that it will zoom in onto some edges or some complex structure. But I haven't wrote the code yet. I'm not very sure what it will look like. And if you see you can see the code called generalized Julia set, and uh, this is and it has some introduction, but this is based on functional programming mainly, but the key part is that it has a Julia set with sensitivity, which which you get from which you get function applied generalized Julia with an R real value array, imaginary value array, and parameters into another array, and in parameter stores the say parameters stores the real and complex part of the each parameter, and you can see from what is done by from there. Uh, sensitivity work RE and IM. Sorry for naming it that, but yeah, that's how I did things basically, and what I did here is that I wrote a loop to to iterate I to iterate the power and real and complex value from this um, to create large number of plots. And the actual plotting function is just these three lines. So these three lines helps to make the same aesthetic or same style of the plot. So if you want to make a plot with the same style that I'm with the same style, background color and foreground color and grid that I'm using, you can always refer to these plots. Uh, but but we but I'm also planning to build this into functions and actually we could create a lot more beautiful visualizations for like other mathematics, say high school mathematics or basic calculus, linear algebra, transformations, and dynamic systems. Um, I'm planning to store the themes to. I'm planning to write the themes, like build the build some functions that help you make the plots with same color schemes and the same styles. And and what I get to do recently uh, create a music actually create a music visualizer with a bunch of things, and what it was doing was quite fun. It was to extract uh, the main the frequency with the highest energy, and by mapping the frequency onto an index plot, and I can import some images of the Julia set in order to in order to create some very fancy artistic stuff. But if you don't want to be too fancy, you better not use fractals because fractal is a pretty dangerous thing to use in art. I think probably and yeah. So let's get to the next part. And so you could and iterations for a linear transformation can also create fractals. Uh, but I haven't done the things for that, and I haven't uploaded the code yet. I just I had a bunch of fun there, and yeah, that's it. So let's get to the next part. And for continuous system, I have, honestly I haven't done much work, but for this one, I'm definitely going to do. Definitely gonna build a new package which I posted on. Uh, I posted one thing on Julia conference. Um, and I argued that I think that the codes can be rewritten and we can build back a better package to utilize some existing package ecosystem to simulate the dynamic system faster and utilize GPU and OpenGL system to and OpenGL to create better animations for dynamic system, and not only better but also faster, so that it could really so that it could help with creating those animations. Um, but um, different plotting package still are still used for different purposes. For example, plot.jl is like used for random easy to create um, exploratory visualizations and some easy illustrations or illustrations for publications and OpenGL is more like a real time stuff, which is suitable for fast and real time rendering, and also some lighting effects. So it's a little bit different from here. And so for this one, I used the plot.jl and to make the animations, but I built my own package for dynamical for initial value problem of dynamical model. So this actually follows an differential equations, which is which people call it the Lorentz system. But what I did there was that I picked a bunch of nearby points to create. So this used to look like a point, but it's actually a point that consists of it's actually an overlay of a number of points uh, that have very close values, and at some point it has and you can see where it has the error gets larger and larger and the error gets larger and it creates band and at some point it has great sensitivity to initial system and no matter how I connect these lines, I cannot predict accurately because like small error of this can create a large effect. But another interesting thing to notice is that no matter how far those points are, they still trace very similar topological structures. So that's quite interesting. And but the problem with this visualization is that I use a linear selection of point. I should actually pick a point and pick using probably spherical coordinates to pick a bunch of points within a little sphere so it could be some kind of area or volume preserving. So that I can actually simulate the error, the what happens to the errors on what happens to the error with the same scale on each variable, which is probably more helpful. Uh, but I've also created like a single point trajectory, which is yeah, which is some kind of more simplified. Um, but if you go to my channel, you could see some more uh, videos about the continuous dynamic system, but mainly they are in development. Okay, so let's get to the C sequence, and this is one thing I've quite interested about, which is from OEIS, and it has a way to create fractals in with inequalities. So we can create fractals with iterative equations, but we can also create fractals with inequalities, and I guess someone made a plot of the sequence with um, and this sequence is called this sequence is called forest fire, and you could Google it. And I'm actually planning to write some function to animate those the to animate and visualize those sequences and in different ways, of course. Mm, but haven't done it yet. And yeah, and there's another package called Serious Explorer Zoo, and made some I don't know how to spell it, but Petrarchian or something sequences uh, mentioned by Hofstadter in uh, 1980, and one mentioned by John Conway in 1988. So John Conway was, in my opinion, he has done a lot of other things he has done a lot of other things that is more interesting than Game of Life, and I think this is one of the example that he created a way to create a iterative sequence that generates fractal. And the first thought is from a book called Fractal Geometry and its Application, which is a Chinese book. I just translated it. It doesn't have I think it doesn't have an English title, but we could, if you're interested in this part, you could see this, but uh, this also shows how we can create fractals out of a sequence. And what this is doing is that it takes a sequence. So the sequence looks like this. Sorry, I can't really. Um, so I can't move this, can I? All right, I'll just move the plot, and I'll just use the presenter view. Uh, yeah. So so this is what the plot look like. So we plotted. So this is what the sequence look like. The x-axis is is the t or the nth term or the tth term, and the y-axis is the value. And what is doing here is I take this sequence and I put it into uh, a software that does um, the uh, periodic periodic analysis and create this spectral density estimation. And according to the book, we should see some widened peaks. I don't know what widened peaks. I mean, the peaks that are wide, maybe they are not exactly the sharp thing that we see on Fourier transform. And we can all we can also see some widened peak on its Fourier transform. On its plot of Fourier transformation, that the peaks are not straight. It is like widened or it has a I don't know how to I don't know how to how to describe it. It's like lots of different um it's like it's got a slope that are not very sharp and yeah, that's what happens when you do Fourier transformation of those aperiodic things, because it cannot really extract an absolute period, and its periodicity and its period occurs maybe, and if they do Fourier transformation, you can't really extract its period. But what's interesting about that was you get same result no matter how many terms you calculate, and that's sort of its self similarity, which says it's fractal. Okay, so we get some non-periodic chaos, mainly some fractional diffusion. I did a yeah. So the title page was that. The homepage was used for that. Um, so I've done 2D, 3D Brownian motions and the Levick flight, and I managed to do this with multiple particles and trace the multiple files, but does look like a screen protection animation in Windows. Uh, so that you could get the ideas that even if like even we when we see randomness as a unique literal word, there are actually different types of randomness, and some has a fractal dimension. And you can see that if you zoom in at one part and still still shows its exquisite structure, which is which was quite amazing. But I haven't read much about fractal diffusion yet, so I can't really explain it uh, in detail. And there's some more recent stuff. As you see, I did the deterministic. Sorry, I did the deterministic map from here, which I created for tint map and logistic map. And the difference between tint map and logistic map is that tint map uses x. It's iterated by 1 - lambda times x, absolute value of x, and this is by x squared. So I'm thinking that if I get x on the lambda on the horizontal axis and x on the vertical axis, this draws a bifurcation map, and this draws another bifurcation map. But can I get some smooth transformation from this to that? Can I like say this is two straight line, this is something bent? Can I get something in between? And can I can I interpolate, and can I can I extrapolate, like can get something more extreme? And I did it, and I did, so that I created the map of the generalized power. I don't know how to name it because I haven't seen this one in any of the books. Like people like don't get really excited when they create fractals out of when they create when they create new fractals, because new fractal is like everywhere, and depends on like whatever creative thing you do to the expressions. And as you see, if I stop from there, this shows a tent map with x assigned to 1 minus lambda absolute value of x, and then increase the p. This is a logistic map, 1 minus lambda x squared, and it could go to the power of 3 to the power of 4, and you can see how this plot is squeezed. And what happens is that we could have a look at the cobweb. So when p is less than 1, you get a bunch of these things. And when p raises to 1, I'm always using the absolute value. So it's 1 minus lambda times absolute value of x times to the power of p. So this is when p reaches 1. And before that, we have a negative, we have a power that is less than 1. Say this p equals to 0.1. And you can see what's happening here. And for logistic map, we get for logistic. Oh wait. Okay, so cobweb by p just 0.7. It gets a little bit different, and and when it becomes more than 1, it's a little bit bent in that way. So it's bent in that way. And it gets closer to 2. You can see that it gets somewhat more similar, but when it reaches 2, you get this one is a smooth. It sort of looks like a smooth curve, and as you increase the power, you just get this thing to be squeezed into another form. Say like p equals to 3 times a. So this part has a large concavity. What we can also do is that we can view the cobweb group by power. Oh, sorry, group by lambda. So if I draw a vertical line from some point of from some location of this plot, say we can get from there. Um, so we first have a look at lambda equals to 1.0. Which I believe is from here. And this shows how the thing evolve at this line as I change the power p. So at this point it has a single point, there's 2 points, and there's a periodic stuff. And large lambda value usually have some more complicated thing. Say 1.4 maybe. And what happens when the concavity changes? Yeah. So increasing the lambda doesn't always get it. Sorry, increasing the value of p doesn't always get it more complicated. Just because, like, it depends on 2 parameters, and so when we talk about bifurcations, um, we can either have a look at the bifurcation with respect to one variable, or we can create some kind of function that maps one variable to the space of lambda and p, and have a look at its structure. Yeah, so that's so far about this project, and I'm hoping to I'm hoping to update this and probably update my GitHub files, and I'll see you in the next video.